Welcome back to our series on zero knowledge proofs. We are now transitioning from theoretical aspects to practical applications. Recall that in our first course, we comprehensively explored the fundamentals of zero knowledge proofs. This included delving into arithmetization, constraint systems, and proof generation. Additionally, we delved into ZK snarks, ZK starks, and bulletproofs in detail. In this second course, we delve deeper into the programming and implementation of zero-knowledge proofs. This course is specifically tailored for developers and programmers eager to create ZKP-based applications and apply ZKP concepts in real-world scenarios. We will introduce you the essential zero-knowledge proof programming tools, covering a variety of languages and libraries, and assist you in setting up your programming environment. Let's begin. We categorize zero-knowledge proof tools into three categories: hardware description languages or HDLs, programming languages, and libraries. Each category has several tools, and every training session will focus on one specific tool. HDLs are crucial for designing ZKP circuits. They are similar to VHDL in hardware design, but specifically used for ZKP. In HDLs, we have to explicitly create wires and constraints. Additionally, HDLs have their own languages, and you should learn their syntax. Programming languages in this field are designed to create circuits directly from high-level language. This means instead of creating a circuit and wires, you can use variables and functions, and the compiler automatically creates the constraint system and wires. However, these languages have their own syntax that you should learn. Libraries, in contrast, help in developing ZKP applications using popular programming languages like Rust or C++. In our course, we will explore the most popular tools in each category, and you will learn a wide range of languages and libraries. In this session, we will explore the Circom language, a framework for creating zero-knowledge proof circuits. The session is structured into two parts. Part 1 focuses on setting up the programming environment, and Part 2 delves into the syntax of Circom. As a quick review from our first course, zero-knowledge proof is a protocol between two parties, the prover and the verifier. The prover needs to show that she has specific knowledge without revealing the details. She starts with secret data, known as the input. After running a program, she generates both an output and a proof. These are sent to the verifier, who examines the proof. If the proof is valid, the verifier accepts the output. Remember, the prover is responsible for handling the input, program, output, and proof. On the right side, the elements available for the verifier's verification are displayed, which include the program, output, and proof. Let's break down the zero-knowledge proof process into simpler terms for developers. We start by writing a high-level language. Next, the ZKP circuit compiler transforms it into a low-level program. The witness generator receives the circuit and private input, then generates a witness. Subsequently, a proof generator runs the code, producing both the proof and the output. On the verifier's end, there is a component known as proof verification. Its role is to check the proof and determine its validity. This streamlined overview aims to facilitate understanding of the core software components in ZKP without delving into technical terminology. The first two tasks are performed using Circom tool, which I have colored in green, while the proof generation and proof verification are handled by Snark.js, which have a different color in this slide. Let's review the actual file formats for the input and output of each software component in this process. The program is written in a file with the extension .circom. This file is fed into the Circom compiler, which generates several files. For our purposes, we use only two of them, a .r1cs and a wasm file. Additionally, the input is written in a JSON file format and then fed into the witness generator. The output file extension of the witness generation step is .wtns. The proof generator receives the witness file and generates a proof and an output in JSON file format. Finally, the proof verification process receives them and verifies the proof. Before we proceed, it's crucial to recall that in some ZKP systems, a key generator is used to create the keys for both the prover and the verifier. With this review in mind, we are now ready to set up our environment. The core tool is the Circom compiler, which is written in Rust. To install Rust on your system, simply go to the Rust website to find the right command and procedure for your computer. To start, we assume that you have a copy of Rust on your computer. Therefore, we start by installing Circom on your machine. To start, we get a copy of Circom from GitHub. We type git clone https github.com/idn3/circom.git. Then we go to the folder cd circom and build the project cargo build --release. Next, we install the project cargo install --path circom. Then we install Snark.js using npm. npm is a package manager for the JavaScript programming languages. It comes bundled with Node.js. To install npm, you can simply go to the Node.js website to learn how to install it on your machine. For this course, we assume that you already have npm package manager on your system. Therefore, we continue by installing Snark.js. I type sudo npm install -location global snark.js. I enter my computer password. Snark.js is installed on my computer. My system is ready to compile a Circom program. Our first program is Fibonacci series. Fibonacci series is a sequence of numbers where each number is the sum of two preceding ones. For example, if the first element in Fibonacci series is 1 and the second element is 2, therefore the third element is 1 plus 2, which is 3. The fourth element is 2 plus 3, which is 5. And the fifth element is 3 plus 5, which is 8. And so on. Now, as another example, if we consider the first element as 1 and the second element as 17, the next element would be 1 plus 17, 18. and the fourth element would be 17 plus 18, 35, and so on. Now assume the prover has a secret X that she does not want to reveal or share with verifier. However, she claims that she knows X as the second element of a Fibonacci sequence, such that the 1000th Fibonacci number is equal to this large number. We put these two elements, 1 and 17, in input.json file and this large number as the output in output.json file. Prover has input.json and output.json files, and verifier knows only output.json file. This is the input.json file on my machine, and this is the output.json file. Now let's go and review the code. Every Circom code begins with the directive pragma Circom. It then specifies the Circom version, which in our case is 2.0.6. Each Circom program contains only one main component. We write our code within a template, like this one, template Fibonacci, and assign it to the main component. Here is the Fibonacci code. For now, let's go to Visual Studio Code and save this code in a Circom format file. This will allow us to proceed and first understand the command for proof generation and verification. Later in this session, we will review the code in detail. So far, we have the Fibonacci.circom file. Now, we will use Circom to compile our code. We have Fibonacci.circom file in this folder. Now I type Circom Fibonacci.circom --r1cs --wasm. After compiling this code, Circom generated .r1cs version of our code. Also, Circom generated a folder called Fibonacci_JS. Inside this folder, you see Fibonacci.wasm and also two Java scripts called generate_witness and witness_calculator.js. So far, we have these two output files. Also, remember, from the previous step, we had input.json file. The next step is witness generation. We first copy the files from Fibonacci_JS folder to the main folder. Copy Fibonacci_JS *space . I move these files to the main folder. I run the following command to generate the witness file. Node generate witness.js Fibonacci.wasm, then input.json, and we specify the file name for the witness. I call it witness.wtns. Enter. The witness file is generated now. So far, we have obtained the witness file. Now, we need to create the prover and the verifier keys using the key generator. We can use either Grout 16 or Planck for this process. We discussed these two methods in course 1, and you should be familiar with their differences. In this example, I will use growth 16, which consists of two phases. Phase 1, powers of tau. Phase 2, circuit-based key generation. The first phase is circuit independent and can be executed using the following two commands. snark.js, powers of tau, new bn12812 pot. I give a name to our generated file, pot120.ptau. When I enter this one, as you see, Snark generated this new file. The second command is snark.js, powers of tau, contribute our first file, which is a pot 120 tau, power of tau, and our new file can be 121 power of tau. I give a name for this version of our code. I enter a random text. Okay, the first phase is done. The output file contains both the proving and the verification keys. Now we can proceed with the second phase using these three commands. snark.js, again powers of tau, prepare, phase 2, pot 121.power of tau, pot 12 final dot p tau dash v. The second command in phase 2 needs the R1CS file. I type snark.js, growth 16, setup, then Fibonacci.R1CS, the generated key file, which is a pot 12 final, p tau, then prover verifier 0.z key, enter. The third and the last command for phase 2 is snark.js, zk contribute, power prover verifier 0.z key, then a new file. I call it prover verifier 1.z key, and the name is first contribute name dash v. I enter a random text and it's done. Finally, we export the verification key using this command. snark.js zkey export verification key prover, then verifier 1.json. The keys are generated. Now that we have generated the prover and verifier keys, we are ready to generate the proof. We generate the proof using the following command: snark.js growth 16 proof then prover verifier1.zkey, then witness.wtns, and we specify the name for our proof and another name for our output file. Okay, the proof and output file are generated. The output and proof have been generated. Now it's time for verifier to begin the verification process. If the proof is valid, the verifier accepts the output. Otherwise, the verifier rejects it. Verifier now verifies the proof using this command: snark.js grout16 verify, then verifier1.json, then output JSON, and the proof JSON. The proof is confirmed. Therefore, the verifier trusts the output. We now understand how to generate a proof and verify it. Let's review how to write a program in Circom. You saw in the previous section that Circom program starts with pragma Circom and the Circom, and it continues with the Circom version, which is in our case 2.0.6. To start execution, an initial component must be specified. By default, the name of this component is main, and only one main component can be defined. We type component main. The main component needs to be instantiated with a template. Templates are the mechanism for creating generic circuits in Circom. They define circuits and their own signals, such as input and output. For instance, template Fibonacci and then here Fibonacci. During compile time, the function argument should be known. Therefore, here I put 1000 and semicolon. Now let's look at inside our Fibonacci template. The arithmetic circuits built using Circom operate on signals. The signals are named with an identifier and declared using keyword signal. Also can be defined as an input or output. For instance, signal input fib1, signal input fib2, and signal output fibn. Remember, signals which are not defined as input or output are considered intermediate signal, like signal C. Here is a list of reserved keywords in Circom that you should not use them as your signal name. Signals in Circom can be either private or public. From the programmer's perspective, only public input and output signals are visible from outside of a circuit, while private input and intermediate signals cannot be accessed externally. By default, the input signals of the main components are private, unless specified as public using the keyword public, like this one. Component main public fib1, fib2 equal Fibonacci 1000. In the previous version of our main component, fib1 and fib2 were private signals and fib_n was a public signal. In this version of our main component, fib1 and fib2 and fib_n are all public signals. This was an example. I go back to our original main component. All output signals of the main component are public and cannot be made private. Also, any other signals within the circuit are private and cannot be made public. Now, let's consider another example. I define another template here. I define it as template fib template 2 and then write signal TMP. Now I go to my Fibonacci template and use the first template. I type component fib, for example, temp 1 equal fib template 2, then fib temp 1.tmp is, I assign it to, for example, fib1. I save this program as Fibonacci 2.circom. Now I go here and compile the code. I type circom Fibonacci 2 circom -r1cs -wasm. As you see, compiler showed us an error. The problem is we are working with an intermediate signal which is not input or output. Therefore, it's private and we cannot access it from another template. The solution is very simple. For example, we put signal input, save it, and then run the command again. As you see, it successfully compiled because now Fibonacci template can access the signal in another template because it's defined as input. Apart from signals, Circom also uses variables. Variables are identifiers that store non-signal data and are mutable. They are declared using the keyword var. Variables can contain either numerical values or the field or arithmetic expressions, particularly when used to build constraints. Let's define a variable here. I removed our previous example and start writing the code with our variables. Variable A equal fib1, variable B equal to fib2, and variable C. Now I compute the Fibonacci sequence. Let's put a comment here. Fibonacci sequence. I write a loop for I from here. I have fib1 and fib2. Therefore, I start from 2, I less than n, I plus plus, C equal A plus B, A and then B. Now let's discuss the signal assignment operation. Signals can only be assigned using double dash or double equal. The safer option is the second one because not only it assigns the value but also it generates a constraint at the same time. I set the output something like fib_n equal to C times fib1. I save and then compile the code and it works fine. Now let's talk about functions. In Circom, functions perform computations and return values or expressions. They cannot declare signals or generate constraints. Use template for these purposes. Every function must end with at least one return statement. Here I define function func1 with 3 arguments n, a and b. Now I can simply move part of my Fibonacci code to this section. return the result, then return C. And then here I replace C with func1 fib1, sorry, and fib1 and fib2. Now we are going to quickly go over the types of expressions in Circom. First, constant values. These are simply fixed numbers like 5 or 7. Next, linear expressions. These are sums of variables and constants like 5 times fib1 plus 7 times fib2 plus 12. The third one is quadratic expressions. These are formed by multiplying two linear expressions. For example, the first expression is this one, 5 times fib1 plus 7 times fib2 plus 12, and the second expression is this one. Finally, non-quadratic expressions. This category includes any expressions that do not fit into the previous ones. For example, I put the previous expression, a quadratic expression, and times fib1. Remember, in Circom, only quadratic expressions are allowed in constraints. So if I make this line a non-quadratic expression, I will get a compiler error. I save this one and then go to the compiler. As you see, I got this error from the compiler. Non-quadratic constraints are not allowed. Now let's review noun and unnown expressions. In Circom, constant values and template parameters, this one here, are always considered noun, while signals are unnown. An expression is classified as noun if it depends only on noun values, but as unknown if it involves any unknowns. For example, when accessing an array element in a constraint, the index must be a noun value. For example, here I define an array called CArray, the size of n, and n is noun in this function, and then I type CArray 0, for example, fib1, and CArray1 fib2. Now let's save and compile the code. Standard constructions are essential for defining the control flow within a program. Here I have already shown you the for loop statement. Now I'm going to show you the while loop statement and if then else conditional statements. So I comment these for and start writing the same logic with while. Now I want to put this inside a if-then statements. If n equal 1, then C equal B. Otherwise, if n equal 2, then C equal B. Otherwise, the while loop. Save and compile. Before finishing this part and going to the next example, the last topic to review is the include command. To incorporate code from other files into a Circom program, the keyword include is used, followed by the corresponding name of the file. It is important to note that the .circom extension is assumed by default when specifying file names. So I write here include inc1 .circom colon and then move my code, this part, to inc1.circom. Then I go back here, save, then compile the code. Coming up in our next video, we will dive into another example by showing you how to write a pseudocode program in Circom. Also, we will cover more features and details about the Circom language. Stay tuned.